we also have one master student, and they will cover topics from what they are doing within our program. And the first student, I think that is Joshua.
So hey,
Joshua Rizzo.
Can you see me? Yeah,
we can see you and we can hear you. So Joshua is a young technical artist. We are extremely proud of him, and he will showcase a pixel art tool for Houdini.
All
Joshua,
right,
you have 6 minutes.
All right, then I'm going to start sharing my screen. Can everybody see my screen? All right.
Yeah, we can see.
So my name is Josh, and I'm a third-year technical art student at BUAS here, and I'm going to present my pixel render toolset that I made as a personal research. But first, a trailer. So this tool allows you to work directly in the viewport and interact with your scene. And you can choose different camera settings. You can orbit your view around. It's pretty responsive. And of course, you can pick your outlines and color them differently. And there's also support for ray trace directional lighting, and you can change some settings there. And point lights are also supported, which you can place in your scene and light your scene the way you want. And in fact, you can put in many of these lights. There's also support for dithering and quite some settings to adjust that, post-processing, like ambient occlusion, height fog, distance fog, and all that stuff. And you can animate it and try out different styles and then export them as you like. There's also some limited functionality for motion blur. And as said, you can export the color alpha and the normals. So why Houdini and pixel art? Houdini, because it's a very powerful combination of scripting and node workflows. You can insert like VEX snippets anywhere, and it's a very nice mix between manual and procedural asset creation. Pixel art, because I stumbled upon this really nice article about the Dead Cells workflow and how they use 2D and 3D together, and it served as an inspiration. And rendering also, of course, would be faster due to the limited resolution. And it's a really nice style to try out automation to get you started with the hurdle of drawing pixel art. How it started is basically I tried to do some ray tracing experiments in Houdini, but these turned out to be super performance intensive, and you needed a lot of samples to get some refinement in there. So I started to reduce the resolution, and pixel art came kind of natural with that. But of course, this is the first prototype that I had. The tool is relatively simple, structured. You have two inputs, and one is the lights that you can put in, and one is the geometry of the scene with the materials. Inside there's a ray tracing segment and the attribute segment, and then you have an appearance and layering segment. There's two outputs, one that visualizes your scene and one that exports your data. The layering is quite easy because it's kind of like Photoshop or compositing. You put in the attributes and you're layering them on top of each other. So to start with the foundation, there all starts by a camera grid, which can either be a Houdini camera or a custom camera grid, which is in the tool. And the normals of these grid points are used for the ray casting. The ray casting is also pretty straightforward in Houdini. In VEX, Houdini scripting language, you have the intersect function, which can give you back numerous attributes like UVW, position, and the hip primitive. And from there on, you can extrapolate all the color and the material attributes. Then there's the ray tracing part of it, where you have first like the directional light, and after the first bounce, it basically tries to look for intersection and towards the light direction. So it's a guided ray tracing in the sense. The same goes for the point lights to make it easier and performant. After the first bounce, they all kind of try to converge to each center of the point light, and the ambient occlusion is also ray traced or ray casted and tries to look for intersection in nearby areas. Then there's the outlines. It's basically, this happens in 2D space where you look for neighboring pixels. One is the silhouette, which is at the border of transparent pixels, which comes in handy if you're rendering out PNGs, for example. Then there's the connectivity part, which checks for different objects of different classes and draws the outline there. And then there's the contour one, which checks, does a distance-based check with a threshold that you can adjust. The bread and butter of the system is actually the attributes and the post effects. Since you can store numerous attributes on each pixel, you can put them further down the system and use them in the post-processing, which happens in the appearance part of the layer. And that makes it so easy to adjust and add new things on top of it. One of the hacky features which took me quite long is the light shafts. And I basically started by looking at the pixels which are the border of shadow and light, and then try to find the average lit surface direction and compare it to the inverse light direction. Then I get the dot product of this, and if it's above 0, I know, okay, this is a place where I can start ray marching in 2D. And then the marching happens, like I said, in 2D, and it gradually decreases. And the stop condition is actually a pixel which is closer to the camera than the initial starting pixel. Some of the use cases for this are sprite animation. You could import your animation and just get go and try to make some sets out of it. Some parallax backgrounds where you divide your scene with the same render settings, and maybe you have a preset. And of course, you can plug in procedural assets because it's still in Houdini, and you can put in your HDAs and everything and render out different iterations to get the look that you want. So what I got away from doing this tool is that too much different functionality isn't really good. I need to keep it consistent. At one point, I had actual shaders in there which were doing like some reflection, and transparency, but this was getting way too complicated, and I needed to really boil down to the core of it. Doing documentation and example files really help finding missing and incoherent features. For example, I added a preset system where you can save out your render presets. And yeah, peers testing your tool is a good way to find unforeseeable problems and fix them. And I didn't anticipate UX and UI taking so long, so there was quite some time I spent on that one. I want to thank you very much for listening, and I want to thank Buas and the organizers for having me, and yeah, SideFX for having such an amazing software.
Thank you very much, Joshua. That was lovely and perfect on time. And I think that our next student should be ready. Who is going next? It's Erwin, right?
Hello.
Hi, Erwin. We can see you and we can hear you. So,
great.
Can you share your screen?
Yeah. Is this visible?
Yeah, perfect. It's visible.
Okay, great.
So Erwin will show us a very important part of making games, that's destructions and explosions. So Erwin, the floor is yours.
Okay, thank you. Hello, my name is Ernst Mega. I'm a third-year visual arts student at Breda University of Applied Sciences, and I focus mainly on visual effects and destruction. Today I will be talking about a destruction workflow I worked on by creating rig hierarchies out of them, and then they can be interacted with in Unreal Engine blueprints. This was the end demo of this research, and I will talk about the goals, the overall workflow I ran through to create this demo. So the concept, I did some research into rigid body simulations, and I came to the idea to create a workflow that separates clusters from an object that then can be puzzled back together in Engine. My main goal being that I wanted to have as much control in Engine as possible, as well as have the RBDs, the art directable RBD functions of Houdini. So why did I choose rigs for this? And my main reason was being, if my simulations would consist out of bones, I would get all the functionality improvements that characters and all the animated assets have as well. And when I especially got convinced to do this because I discovered the animation blueprint system and how much control I would get if I could implement my destruction system in this. So before simulating, I first manually select some clusters into the asset and then fracture these clusters based on their material ID. I then create a ring around each cluster that serves as a containment ring so the clusters don't fall down before the RBD objects hits it. Because this is one object, it creates actually a perfect puzzle piece that can be fit back to the building later on. So initially, I wanted to export these clusters separately through Unreal using the RBD to FBX tool in Houdini. But in Unreal, this gave a lot of separate meshes and cluttered up my maps quite fast. And it also resulted into quite a lot of repetitive blueprint actions to make them interactable. So I went back to Houdini and I first cleaned up the pieces, as each piece in the distribution simulators resembles one bone. And with bigger buildings, this spiked up rather fast. And because the rings around the pieces were not simulated, they became one packed mesh. So I could easily extract this and put it back to the main building, reducing the bone count drastically. Then to create a rig, I loop over each cluster after the simulation, and I make a cluster parent for each cluster, and then merge these cluster parents back to the pelvis, where the pelvis has all the static meshes attached to it. And then the pelvis gets back to the wood bone, creating the rig. And this, I could export this as a skeletal mesh through Unreal. To split the RBD simulation, I use animation blueprints. For each state machine in animation blueprint resembles a cluster. I then set a transition rule that checks if a cluster is activated, therefore playing the animation. And to make this more modular, I create child blueprints that only need a skeleton and an new animation asset to work with different buildings and rigs, as long as the names of the bones are consistent. Then I create a controller blueprint that stores the cluster bones, and with those bones and locations, I could set up a spline tool that creates pathways towards the building clusters. This was extremely helpful, as for different iterations and simulations, I didn't need to set up new splines every time I exported it to Unreal. It then picks one of these clusters randomly as you press play, and sends that cluster towards the animation blueprint, therefore activating the animation machine state, playing the needed cluster or the activated cluster. That ends the workflow for the buildings. Currently, I am exploring multiple ways to use this system and came up with this bridge example, where I divide different pieces of the bridge into clusters and exporting them to Unreal, where I can check the distance towards each cluster from the player and reassemble, and basically inverting the destruction simulation in engine, creating the reassemble effect, as you can see here. For the future, I want to still check out some other scenarios and topics. For example, creating the splines, as you saw before, during playtime, where the player shoots at a set cluster and then it creates the spline on the fly. And I also still want to try out destruction stages, where it checks if a certain destruction simulation of an object played, and then maybe plays a separate animation when it gets activated again. Thank you for having me here. Yeah, I hope you have a nice day further.
Thank you very much, Erwin. By the way, we will have a Q&A for the student sessions. It will just be at the very end of the session. So 2 more sessions, and that's when we will have the Q&A. And I would like to invite the next student. I think that's Peter.
Yeah, can you see and hear me?
Yeah.
All right. All right, does that work?
Yeah, we can see your screen. So Peter will showcase 2 tools that were built in Unreal with help of Houdini engine. And he will tell us how they are used to make one of our year 3 games, which you can check out on Steam.
Yeah, hi. So I'm Peter Pickarz. I'm also a 3rd-year student, and I'm mostly working on procedural environment tools. And in this presentation, I'm going to show 2 tools for the game teams. One is a procedural Norwegian House Generator, and the other one is a Mineshaft and Cave Generator. And I'm going to focus on Houdini Engine v2 for Unreal, affected these tools, and how the new possibilities for user interaction have been used. So the first tool is a procedural Norwegian House Generator. It takes blockout input, and you can decide where the doors go. And the snow gets simulated, which also blends the floor to the terrain. Yeah, the tool itself doesn't make use of session sync, but I use session sync a lot for while creating the tool. And that has huge advantages because you get immediate visual feedback when you change something. It updates in Unreal immediately. It's really quick to make iterations, and it's really fast for debugging because you can actually see what's going on inside of your Houdini engine session without opening a debug file or anything. Now, as for why we used blockout geometry, it's quite easy to customize, and you can create a lot of variation because, I mean, ultimately you can create houses with any shape you want, and it's really fast to set up. So as you can see, there's just two boxes that are put in level, then the HDA is added, some parameters are changed, the boxes are selected as the input, and then a third box is added that decides where the door goes. And yeah, it just takes a few minutes to create a house with this. And inside of Houdini, dealing with blockout geometry is actually quite simple because the SideFX Labs tools have useful nodes for that. So the dissolve flat edges node pretty much cleans up the topology you get from Unreal. And then split primitives by normal is really cool because you can easily isolate the walls, roof, and floor to work on that. One really important thing is snapping the floor height because you don't want the user to end up fiddling around with aligning the floor accurately for ages. And then one thing that I would really recommend anyone working with session sync is to move things to the center at the start and then move it back when you're finished generating something so that it's not floating around anywhere in space, but is always at your center when you're working with it. Now for the other tool, it's a Mineshaft and Cave Generator. It's for a survival game in the Atacama Desert. And essentially it's a spline-based tool that creates caves and mineshafts. And you can also create rooms with BSPs. I decided to go with a viewer state and session sync here because the team wanted a lot of customizability on local points of the curve. Yeah, wanted to be able to adjust essentially parameters per point. For the BSP rooms on the technical side, it's pretty similar to the house tool as well. So it just gets cleaned up, the wooden structure is generated, the walls get a bit deformed, and afterwards it's merged with the system that also generates the tunnels, so that transitions are smooth. As for the viewer state, that is a bit more complex. So more or less it's a spline tool, but it allows intersections, and it's very shortcut based in the viewport. So the user actually spends the time inside of the viewport, and you can adjust parameters per point. And also you update the geometry with a shortcut, which makes it much more editable, easily to editable in the viewport. And of course, because of that, you need guide geometry. So these blue lines here and the points, because the mineshaft isn't always where your splines are, unless you recook. Here you can see what's going on with the parameters. So essentially, the viewer state manages a multi-palm that has an instance for each point, and then each point has another multi-palm with instances referencing to the neighboring points. And then that data gets read by the network, and the mineshaft and cave gets generated based on that. So a few lessons learned. Only because you could let the user control something doesn't mean you should. And what I mean by that is that viewer states and session sync in general pretty much allow you to do anything with the input. But at some point, it gets too much and it takes too long to adjust an instance of the tool. A good idea to look at if you want features for your viewer state and you're not sure how to do it is to look at the SideFX Labs tools, because a lot of them have viewer states and they're quite helpful. And multi-palms with session sync can still be a bit buggy sometimes. Jason is your friend, use it to back up stuff. Yeah, thank you for listening. And yeah, you can ask questions after the student showcase is over, I think, right?
Thank you very much, Peter. That was lovely, and we already read in the chat that your houses are authentically Norwegian, so you get a pass from our audience. And the next student speaker is Luca.
Can you hear me?
We can hear you.
Can you also see me?
We can see you. You can share your screen.
Start sharing the screen.
Luca is a recent graduate and he's currently in a master program. He's also helping us a bit with teaching. So thank you for that, Luca. And we will go in a slightly different direction. So Luca will go a bit into deep learning and how he applies that into animation.
Yeah, this is an ongoing research, small disclaimer. So welcome to my presentation. Sorry. Welcome to my presentation on my master research on quadrupeds animation from videos. I'm Luca, a master student here at BUAS. Previously, during my bachelor, I focused on building tools and exploring procedural generation techniques. Today, I'm working with machine learning for content creation, and this is what this presentation is about, which brings us to the dog on the screen. Kini, a friend's dog, which is helping with my research. The goal is to bring Kini's motion in a virtual environment. Traditionally, you go through many steps in order to animate a dog for a game. For example, you create the model, a skeleton, rigging it, skinning, and animating it. After the animations are done, we also need a system that, based on input and gameplay rules, outputs the desired animation. This is often achieved through state machine system, where we need to define every reaction to each situation. This can be very complicated and quickly becomes hard to edit due to the multi-layer structure, which is not ideal. A solution that in recent years addressed some of these constraints is motion capture, also called mocap. This solution allows developers to avoid handcrafting the animation. Instead, what we do is recording sessions of actors performing the desired actions using mocap equipment. This allows for more realistic movements, which, in some cases, like sports simulation games, are crucial to provide the desired feel, like for FIFA from EA Sports. Mocap has precise requirements, like actors wearing a mocap suit with markers and a mocap studio equipped with specific cameras for accurate results. This is not feasible for all companies, which is one of the reasons for this research. And while for humans, performing the required emotions is not such a big hurdle, for animals, it is an entirely different question. For this reason, especially for movies, often animals are replaced by humans, like the video on the right. Already trained animals or pets might struggle with performing the required motion when put in such environments and situations, resulting in unnatural movement. On a completely different scale is when we want to do mock-up of big animals, or even worse, if our subject is a wild or endangered species, which requires an even more complex setup and comes with logistic issues. In my opinion, for realistic performance, we really need to capture them in their habitat, especially for wild animals, which is not possible through mocap. Through help comes the vast amount of data on the internet. Between documentaries and YouTube videos, we have far more data than what is affordable to capture with mocap. This is even more true for the more problematic type of animals I mentioned before, like this Sumatran tiger on the right, which is an endangered species, which is the other main reason for my research. But how can we convert views to data that can somehow replace mocap? In recent years, pose estimation, which is a branch of computer vision, and consists in extracting their 2D or 3D pose from a single or multiple cameras, grew substantially. This is primarily due to the growth in machine learning techniques and, in particular, deep learning. Thanks to the massive amount of data available and increasing compute, they produce awesome results in this field and others. So this is how we will extract the motion from the video. But how are we going to use it, use an animation? So reinforcement learning comes to our aids and recently proved to be an excellent solution to solve tasks where it is not easy to formulate an equation to evaluate the current results, but we can more easily define goals, such as reach certain location by walking. It works to trial and error and supplementing rewards to our agent based on the defined goals. Reinforcement learning achieved excellent results in the past few years, from learning to play games to learn how to do certain actions like walking. To put it all together, I'm developing a pipeline for my master thesis that from a video extract 3D pose for each frame. From there, a motion trajectory is calculated to enforce temporal consistency between each frame. Then the extracted motion is provided alongside a physical character, like a ragdoll, to a reinforcement learning-based framework that learns by imitating such actions. Finally, a mapping between input animation is learned. The goal of the motion estimation step, which is the first big step in the pipeline, is to extract 3D motion from our video. To achieve this, first we extract 2D information from the video in the form of 2D joints, location, and silhouettes. And then we use differentiable rendering technique, in particular skin multi-animal linear model, SMAL, which leverages this 2D information to fit a deformable mesh that was previously learned on multiple animals. The motion learning step instead is based on reinforcement learning and uses imitation learning techniques to transfer our provided motion into a ragdoll character. Physics-based character and environment are used to better generalize the character-environment interaction. On the left, you can see the model, the agent trained on a very short clip that I showed before. On the right, the one trained on mockup from the original paper. This, of course, needs very specific movements, and I want to share the ones used with the code for reproducibility. And that's why I need the help of Kini. So hopefully soon I'll get enough videos to bring the motion from Kini into a virtual environment. But stay tuned, because I'm still working on the thesis. I will publish more about it in the upcoming months alongside the GitHub repo. And I am going to try to submit to a conference or release it in a paper-like format by the end of the year. This work just builds on top of many other researchers. And it's just the first step into this direction. Thank you for listening. And thanks to GUAS and the organizer as well for inviting me to talk.
Thank you, Luca. That was really interesting. It's indeed amazing just to see those things in motion. I remember, I think it was 2006 when we first saw similar research from Disney coming at FMX in Germany, and it was only 2D and it already looked like magic. And now, only a few years later, we are seeing it in 3D and combined with motion capture data, so not only reinforced learning. So fantastic. The way that we will now do the Q&A, I will ask all the participants of these micro talks, so all the students, to turn on their camera and their mics, and we will do the session with raising hands. So whoever has a question, raise your hand and start your question with addressing the person that you want to ask.
Am I still sharing the screen? Sorry, but
yes, you are.
I cannot find the control to stop it.
I don't think you can. I think that will be something for our team to do.
Okay.
Yeah.
Oh, here. Hi. So a question to Peter. I think it was Peter who did procedural houses and paths with the multi-parms and everything.
Yeah.
So I wanted to ask, did you write some kind of wrapper library around the Python functionality for multi-parms? And
well, not really. I mean, I wrote some functions to essentially, because in the end, in the viewer state, you often do things like removing a point, removing a connection, checking for neighbors and whatnot with the multi-palms. So I made functions for that I then reuse, but I didn't like invest too much time into it, honestly.
Makes sense. And you had then into that built in this JSON system to kind of back up your inputs. Is that right?
Yeah, so I mean, essentially the only problem there is that multi-palms sometimes bug out a bit with session sync. Yeah, then I just made it so all the data that the user sets up gets saved in JSON, and then there's a button to load that back in should the data get lost by session sync when saving the level. It's just like a thing to be a bit careful with session sync, because sometimes it can lose track of data.
Very nice. I especially like the connecting network stuff that you do with the what is it called? Viewer state. And I would love to see the code if you could ever make it publicly available, or the tool at all.
Yeah, I think I can do that, definitely.
Cool, thank you.
Hello, I've got a question for Erwin. And the RDB simulation was pre-baked, right?
Yeah, it was pre-baked. Yeah.
Yeah. I was asking myself if you have an opinion about vertex animation texture without what are the benefits and disadvantage of this against classic FBX animation?
I actually used vet textures as well in a previous project, and I think with this system, the main benefit I get is that I can make one RBD simulation in Houdini and then split it in Unreal. Well, if you have a vertex animation, all the points are laid out and then just played out. So I have more control in Unreal, I would say. Also with the blueprint functions, I guess.
Yeah, I guess with animation, you can start with the classic animation and finished the RDB simulation with the Unreal Physics system, for example.
Yeah.
Okay.
That's also a subject I still wanted to look into by combining it with physics.
Okay. Thank you.
Yeah, no problem.
Hello. Hi, I have a question for Luca. That was an awesome talk, and the presentation was really cool. So I wanted to ask, what kind of harness did you, or are you planning on using to drive the reinforcement learning step? Like, are you using some prepared engine, and what is it? And also, are you leveraging any existing ML libraries in that context? Thank you.
Yeah, so for the reinforcement learning step, there was actually on the slide a reference to a paper, which is the one I'm mostly using for it, which is called Carl. Like, the short name is Carl. I can send the link later if you want. And it is based on TensorFlow 1.x, I think, and uses Bullet for rendering, Bullet for the physics and the rendering part. So it is a combination of C++ and Python tools, frameworks going on there. So yeah, that's it. That's where it comes from. It is actually, sorry.
Oh, no, please go ahead.
No, I was just saying that it's actually a step forward from another research from a few years ago that was called Deep Mimic, and uses the same framework that was built from that one and just advances it to make it more oriented towards locomotion, because Deep Mimic was just about any type of motion, while this one instead is very focused on locomotion because it has The steps are for speed control and adding control, and as multiple steps, and in each step they learn both. So it learns how to change velocity based on the provided motion, and learns how to turn left, right, based on the provided motion again.
That's fantastic. Thank you very much. If I may sneak a small mini question, did you do any C and C++ work on this, or is it just Python?
No, myself, I only did Python work because again, this framework was already built. Unfortunately, for the master, it's only 1 year, so there was no chance of building everything on my own. Yeah, so on my side, just Python. But again, the system, it's built in a combination of C++ and Python.
Perfect. Thank you very much.
You're welcome.
Yeah, as far as I can see, there are no more raised hands. So I want to thank all of you guys for the presentations and for really keeping it within the time slot, which I'm certain that it was a big challenge because there was so much to cover and so little time to do that. And for all the companies that are there in the stream, I want to mention something, that these guys are looking for internships already. So if you feel like this kind of talent would be useful in your team, just ping them, and you know, we will arrange something. We will move then